indefinite integrals using U substitution. So U substitution can be a little bit tricky, but the more you practice this, the more examples you see, kind of the easier it becomes. So the top of the page here, I have a little step-by-step process for you guys with an example next to it. So really the idea is we're looking at an equation that we cannot integrate the way it is, or to algebraically manipulate it would be pretty cumbersome, pretty difficult to work through. So we're essentially using like a reverse chain rule to integrate the function. Now, if you remember, chain rule is d outer times d inner. That's kind of like what we're looking here with like the u and the du, these two pieces. It's the outer function's derivative times the inner function's derivative. But we're reversing that process, and we use this method called U substitution to make that work. So let's take a look at a few examples in here. Right, we'll kind of go step by step with a few of these to kind of take a look at and see what it would look like. So typically your U substitution is going to be that inner function. So in my case here, I'm going to substitute U and I'm going to make it 3x minus 4. Now when you find your U, you do want to find the derivative of that. So the derivative of 3x minus 4 is 3 dx. Now the reason why we want that derivative is we cannot integrate the function the way it is without manipulation. So what we're saying is, well, you know what? If it was just u to the fifth, that would be easy. We can integrate that and have no problems. But if we're adjusting the variable to go from 3x minus 4 to now being a u, we need to be able to solve for dx, right? So divide both of these sides by 3 here and find out that, hey, you know what? dx in terms of u is equivalent to du over 3. So that way we could substitute in for that dx. Now, a lot of times here, we find that it's easier to integrate by, I usually find that it's easier to bring that 1/3 to the front. You don't have to, but we're going to integrate u to the fifth du with that 1/3 up front. Now, when I integrate that, I'm going to have 1/3 times u to the sixth over 6 plus c, which is equal to u to the sixth over 18 plus c. Our final step of U substitution is going to be to substitute the x's back in. So our final answer for this would be 3x minus 4 to the sixth power over 18 plus c. And that's how we work through U substitution. All right, another example for you to take a look at. This time we have a little bit more going on with this equation, but again, we're looking for that inside function. So in this case, it's going to be that x cubed plus 4. So I'm going to set u equal to that piece. So we have x cubed plus 4. And when I find my du, I find that that's 3x squared dx. And again, solve for that dx. So we divide that 3x squared over. We're going to have du over 3x squared is equal to that dx. Now, when we're integrating these pieces here, we have 6x squared times u to the fifth power, right? That's what we've substituted. And then when we substitute in for the dx, we have du over 3x squared. Now, a really important piece that we're seeing right here is that the x's. Now, if you notice, there's the x squared and the x squared. Those can reduce out, and they have to reduce out. If you are trying to do U substitution with integration, you cannot have x's and u's together. So we expect that to happen, and if it doesn't, we have to make adjustments. And then what's also nice here is that the 6 and the 3 can reduce to a 2. So what we're really doing is integrating 2 times the integral of u to the fifth du. Now, again, kind of working through that process here, that's really just 2 times u to the sixth over 6 plus c, which when we could reduce this to a 1/3. And then when we substitute our u back in, it's going to be x cubed plus 4 to the sixth power over 3 plus c. So another example here of that U substitution. So we're going to keep going through some more examples here. Again, the more you see, the easier these become, the easier it is to kind of figure out what U is and so on. So number 3, we have the square root of x minus 1 squared over the square root of x. So again, we're going to pick that inside piece right here. So I'm going to say my U is equal to the square root of x minus 1. And we also know that with these, it's easier for us to integrate with and derive with fractional exponents. So I'm going to just change that to x to the 1/2 minus 1. And when I find my du, I get 1/2 x to the negative 1/2 dx. But then solving, a lot of times I find it easier to be working with the radicals and positive exponents. So I'm going to rewrite this thing as du equals 1 over 2 radical x dx. And as I solve for dx, I actually want to multiply by 2 radical x. So 2 radical x du is equal to dx, right? So that part's actually going to become pretty important here when we throw our u in here. So we're really integrating u squared over radical x. And when we substitute in the dx, we have 2 radical x du. So again, nice piece here is those radical x's cancel, and then we just have that 2 left over. So we're really integrating 2 times the integral of u squared du, which, right, u squared is nice and easy to integrate. It's really just 2 times u to the 3rd over 3 plus c. And then when we substitute in our u, you could put the radical back in or keep it as x to the 1/2, but it's really going to be 2 times, in parentheses, we have our radical x minus 1 to the 3rd over 3 plus c. Right, and we have that next u substitution here. Pretty cool. All right, number 4. This one, sometimes you start to see trig functions in here and exponential functions. Typically, again, there are multiple ways to do this example, but the way I'm going to show you guys is I'm going to say, hey, look, that exponent is kind of like our inside function. So I'm going to make my u the cosine of x. So the derivative of that is the negative sine of x dx. And as we solve for that dx, I'm going to divide that negative sine x over, and we could find out what dx is equal to. Okay, so now we'll start substituting in. So I'm really integrating the sine of x times e to the u and du over the negative sine of x. So our sine x's will cancel, and just don't forget that negative 1 there. We're going to bring that to the front. I'm going to say the negative 1 times the integral of e to the u du. Now the integral of e to the u is just e to the u. So I have negative e to the u plus c, or in our case, it's just negative e to the cosine of x plus c. All right, so again, starting to kind of see what u would be, and this thing is starting to take shape a little bit. Now again, another example with a trig function here, we have the integral of the cotangent of 3x dx. Now cotangent does not have an integration rule, but what we do know about cotangent is this is really just cosine of 3x over the sine of 3x. And sometimes it's not really an inner function that we're going to use as our u, but rather one of these two functions here. So what I'm going to do is I'm going to pick my, sometimes you have to do trial and error. So we'll pick one of these two things to use. In my case here, what I'm going to do first, I'm going to just try to pick cosine. All right, so I'll say u equals cosine of 3x. So that means du is equal to negative sine of 3x times 3 dx. So as I solve for this, I have du over negative sine 3x times 3, which equals dx. Now this is kind of where it starts to get interesting, because as I'm integrating this, I'm really, what I said was u is equal to the cosine of 3x. So this would be u over the sine of 3x times du over the negative sine of 3x times 3. Now, if you notice, those signs will not cancel out here. So since those signs don't cancel out, really what that means is one of two things. One, u substitution will not work for this problem, or two, I just picked the wrong u substitution. So I'm going to go back here. I'm going to kind of erase this and we'll start back over. And what I'm going to do is I'm going to take a look at the sine, right? Let's try the other one, right? So if I say u is equal to the sine of 3x, and I found the derivative of that would be the cosine of 3x times 3 dx. And as I solve for this, I have du over 3 times the cosine of 3x that equals my dx. Now when I substitute in, this one's pretty cool. We end up with the cosine of 3x over sine of 3x is my u times du over 3 times the cosine of 3x. And now we'll start to see something cancel. So just because it doesn't work the first time doesn't mean it won't work eventually. So sometimes it's just a little bit of that trial and error process. Now we bring out, right, as we reintegrate this one, I'm going to just rewrite this down here. We end up with 1/3 times the integral of du over u, or it might be a little bit easier for you guys to think of this as 1 over u times du. That du is often written in the numerator, but again, sometimes it's easier to see it off to the side. Now, what's really cool about this one is when we integrate this, this is going to become 1/3 times the integral of 1 over u is the natural log of the absolute value of u plus c. And when we substitute this back in, our final answer is 1/3 times the natural log of the absolute value of the sine of 3x. Let me make that more like an absolute value, and then plus c all the way at the end. So again, pretty interesting, pretty cool way of u substitution, but they can sometimes get pretty tricky here. All right, number 6. This one I think can start to get a little bit trickier and a little bit more difficult to work with. So this one definitely has like a clear inside function here with the x plus 1. So I'm going to say u equals x plus 1. That means du is equal to dx, which is awesome. Very simple for us to work with. So when we're integrating this function, we'd really be saying, hey, this is x over the square root of u, or I'm going to make this u to the 1/2 power, and that's just a du. Now, if you notice, there's a big problem here in the sense of there's nothing to cancel out. Now, sometimes when that happens, it means we have the wrong u. Other times when that happens, it means we can kind of rearrange this problem a little bit to make it work. So in our case, since we know u is equal to x plus 1, one thing we can do is we could solve for x. We could say, hey, let's subtract this one over. We have u minus 1 equals x. And now I can substitute in for this x. So what I end up with is the integral of that x becomes u minus 1 over u to the 1/2. Now du. Now, a couple of things we could do here is I can divide these two terms. So I could say, well, this is just equal to the integral of u over u to the 1/2, which would be u to the 1/2 power, minus 1 over u to the 1/2, which would be u to the negative 1/2 power, du. And as we integrate this, we would end up with u to the 3/2, and then since we divide that by the new exponent, same as multiplying by the reciprocal, minus u to the 1/2, positive 1/2, divided by 1/2, or times 2, plus c. So our final answer on this one, when we substitute that u back in, is 2/3 times the square root of x plus 1 cubed, right? Just rearranging this problem a little bit, minus 2 times the square root of x plus 1 to the first, and then plus c all the way there at the end. So again, that one's pretty tricky, but that is an option for us, is sometimes we can manipulate our variables a little bit. All right, another tricky problem for us, and the last one we'll talk about today, is sometimes we have our arctrig functions that come and take place here. So in this example, it might look like a good u substitution for us to work on would be 1 minus 4x squared. But as we try to do this, you don't have to write this one down. This is not going to work. So as we try and do this, we have 1 minus 4x squared. And when we have our du, we get a negative 8x. Now, if I were to bring that dx, if I were to bring that back in, I know nothing's going to cancel there. So I'm just going to stop right here and say, okay, that wasn't my right u. What else could I do? And another thing you can do sometimes is kind of get that sense of, this thing looks a little bit like the derivative of inverse sine. Right? The derivative of inverse sine of x is equal to 1 over the square root of 1 minus x squared. And that's kind of modeling what we see here. Now, I think the key on this problem here is that when we're looking at it, this piece right here needs to be rewritten. So we're going to rewrite this thing as 1 minus, instead of 4x squared, we need something entirely to be squared. So in our case here, I'm going to throw parentheses, and the square root of 4 is 2, so I can rewrite this thing as 2x inside this parentheses being squared. Now, what that does for us is it allows us to find a u for u substitution. Now I have kind of like this true inner piece here. It's like a multiple inner piece. And I'm going to be able to say that u is equal to 2x, which means du is equal to 2 dx. And if I wanted to substitute in, du over 2 is equal to our dx. Now, as we integrate this function, what that really means, I forgot my dx here earlier. What that really means is I'm going to be integrating 1 over the square root of 1 minus u squared times du over 2. Now, the beauty of this problem is this now much closely models the derivative of that inverse sine function. So now we know we can integrate this thing and get that inverse sine function. So I'm going to rewrite and bring that 1/2 out to the front. We're integrating 1 over the square root of 1 minus u squared du. And when we integrate that, we already said we're looking for that inverse sine of u, and then we have that plus c at the end. Now, when we substitute our u back in, we find out that our answer is 1/2 times the inverse sine of 2x plus c. There we go, we have that final answer. So u sub takes a lot of practice and a lot of kind of manipulating and working through these integrals and derivatives. But once you start to get a hang of it, it does become nice and easy. So keep at it, keep looking at some of those practice problems, and if you need to work on some corrective assignments, make sure you do that.